sorting looks simple. Just arrange numbers from small to large. But here's the thing. Different algorithms solve this exact same problem in completely different ways. Some are slow but simple. Some are fast but harder to understand. So let's make this a race. 5 algorithms, 1 messy array. By the end, you'll know exactly how bubble, selection, insertion, merge, and quicksort actually work. So what is sorting? At its core, sorting just means arranging items in a specific order, usually smallest to largest. And you rely on it every single day. When you sort your marks from lowest to highest, when Amazon shows you products from cheapest to most expensive, when Google ranks search results, that's sorting. And it's not just about looking neat. Sorted data is faster to search through, which makes it one of the most important ideas in all of computer science. Before we start the race, how do we decide which algorithm is better? We look at a few things: how many comparisons it makes, how many swaps or moves, how much time it takes as the data grows. That's time complexity. How much extra memory it needs, space complexity. And one more: stability. Imagine 2 students with the same marks. A stable sort keeps them in their original order. An unstable one might flip them. Keep these in mind. There are scorecards for every algorithm. First up, bubble sort. The idea is beautifully simple. Walk through the array, look at 2 neighbors at a time, and ask, are you 2 in the right order? If not, they swap. Let's go. 7 and 3. 7 is bigger, so they swap. 7 and 5. Swap again. 7 and 2. Swap. 7 and 8. 8 wins, no swap. 8 and 1. Swap. And notice what just happened. The biggest number, 8, bubbled up all the way to the end. It's locked. We repeat this pass after pass, and the sorted zone grows from the right. It's easy to understand, but slow. For every element, we may scan almost the whole array. That's big O of n squared time, with big O of 1 extra space. Next, selection sort. Instead of swapping neighbors over and over, this one is pickier. It scans the whole unsorted part, finds the single smallest number, and places it at the front. Watch. We scan everything. 1 is the smallest. Swap it into position 1. Locked. Now scan the rest. 2 is smallest. Lock it. Then 3, then 5, and so on. The big advantage? It makes very few swaps, at most 1 per pass. But it's still slow because it scans the array again and again. That's still big O of n squared time, big O of 1 space, and by default, it's not stable. Now insertion sort. And this one will feel familiar. Ever sorted a hand of playing cards? You pick up 1 card at a time and slide it into the right place. That's exactly this. We treat the first element, 7, as already sorted. Pick the next card, 3. It's smaller than 7, so it slides in before it. Pick 5. It goes neatly between 3 and 7. Pick 2. Now we shift the bigger cards right to make room and drop 2 into place. Each new element finds its home in the growing sorted hand. It's simple, it's stable, and here's the magic. If the data is already almost sorted, it's incredibly fast, close to big O of n. Worst case, it's big O of n squared, but for small or nearly sorted data, it's a star. So far, so good. But here's the catch. Bubble, selection, and insertion all share one weakness. With 10 numbers, instant. 100, fine. But 10,000, a million? They crawl. Their work explodes as the data grows. To sort big data, we need a smarter idea. Instead of fixing the whole mess at once, what if we broke it into smaller pieces? Meet merge sort, our first smart algorithm. Its philosophy? Don't sort the whole thing at once. Break it down. We split the array in half, 7, 3, 5, and 2, 8, 1. Then split again, and again, until every piece is just a single number. and a single number is already sorted. Now comes the clever part, the merge. We take two small sorted pieces and zip them together in order. 3 and 7 become 3, 7. 2 and 5 become 2, 5. We keep merging upward, always picking the smaller front element, until everything combines into one perfectly sorted array. The beauty? It's always big O of n log n, fast and predictable, every single time. It's stable, too. The trade-off? It needs extra space, big O of n, to do the merging. When you need guaranteed performance, Merge Sort delivers. And finally, the algorithm most languages use under the hood. Quick Sort. Here's the idea. We pick one element as the pivot. Let's choose 5. The pivot becomes a referee, standing in the middle, giving one rule. Smaller than me? Go left. Bigger than me? Go right. So 3, 2, and 1 move to the left. 7 and 8 move to the right. And just like that, 5 is in its final correct position. Everything left of it is smaller. Everything right is bigger. Now we do the same thing again on the left side and the right side, recursively, until everything's sorted. In practice, Quick Sort is blazing fast, usually big O of n log n on average, with very little extra memory. The catch? If you keep picking bad pivots, it can slow down to big O of n squared, and it's not stable by default. But for fast, in-memory sorting, it's the champion. Let's put all 5 side by side. The simple sorts, bubble, selection, insertion, share that big O of n squared average. Easy to learn, but they don't scale. Then the smart sorts, merge and quick, hit big O of n log n, handling huge data with ease. Merge Sort is steady and stable, but uses extra space. Quick Sort is faster in practice, but less predictable. Notice the pattern. There's no single best algorithm, only the best one for your situation. So which one should you reach for? Just learning the basics? Bubble Sort. Worried about expensive swaps? Selection Sort. Small or nearly sorted data? Insertion Sort. Needs stable, predictable performance? Maybe on linked lists? Merge Sort. Fast in-memory sorting? Quick Sort. And if you're working with priority queues, that's Heap Sort, another big O of n log n option I cover in a separate video. Here's the honest truth. In interviews, you should understand all of them. In real projects, you'll usually just call the built-in sort function, but knowing how these work is what lets you understand performance, and that's what makes you a better engineer. Quickly, what does this look like in code? Bubble Sort is the easiest place to start. 2 loops, 1 comparison, 1 swap. That's it. For the smarter algorithms like Quick Sort, the logic is recursive. Pick a pivot, partition, then sort both halves. I'll keep this short on screen, but the full Python and Java code for all 5 is in the pinned comment and on GitHub. Pause here if you want to read along. Let's lock it in. Bubble Sort. Swap the neighbors. Selection Sort. Select the minimum. Insertion Sort. Insert into the sorted part. Merge Sort. Divide and merge. Quick Sort. Pivot and partition. 5 strategies, 1 goal. If sorting finally makes sense now, subscribe to Code Clarity DSA. In the next video, we'll make recursion just as clear.